Hello everybody, welcome to the first video dealing with the Bohr model of the hydrogen atom. So I'm looking at the summary notes where we list the so-called four postulates that Bohr made when he modeled the hydrogen atom. But before we look at these, I want to talk a little bit about the history of atomic models to set the stage. So let me go to our notebook here. I just want to sketch some pictures and mention some names. Again, I'm not going to test you guys on this, but it's interesting, I think, to talk about this, to see, in a sense, how radical the Bohr model was. And it must have something to do with photons and quantum optics, and it does. Okay, so let's see. Late 1800s, around 1860 or so, people have a fairly good value for Avogadro's number. Now, what's important about that is if you have Avogadro's number, then you have a approximate volume for an atom, right? Because you know the number of atoms per mole. You can get a sample and determine approximately how many atoms or molecules, right, are in that sample. And knowing the dimensions of the sample, you can then get an approximate volume for the atom. So people know that the atomic size is on the order of few angstroms for a typical atom. Okay, hydrogen is around 1 or 2 angstroms depending on where the electron is, and then bigger atoms, of course, are larger in size. So we know that the atomic size, and I mean approximate diameter, we are on the order of a few angstroms. And the angstrom, remember, this angstrom is a special length unit that we like to use, in fact, because it is on the order of atomic dimensions, so a few angstroms. So I remind you guys that 1 angstrom is this special distance of 1 times 10 to the minus 10 meters. Okay, so an angstrom is 1/10 of a nanometer. Okay, so we know the atomic size is roughly a few angstroms. All right, so then late 1800s, a guy named Thomson, British scientist, he makes a measurement, does an experiment, and postulates the existence of the electron as a tiny charge-carrying particle. And the electron gets tagged with negative charge historically. So we now have the idea of the electron as a negatively charged particle. So we have the electron. Now, people know that atoms are neutral unless you ionize them, right? You can make them charged. But atoms usually are neutral, so if the electron is negatively charged, there has to be some positive charge also in the atom. All right, so Thomson puts forth what he calls, or what is referred to as, the Plum pudding model. Again, he's British, so what's a plum pudding? It's this pudding where embedded in the pudding you have plums. And what the Plum pudding model says is, okay, you have this volume that is the atom. The positive charge is spread out over this entire volume. So this whole volume, the pot is filled with this positive charge stuff. That's the pudding. But embedded in this pudding, you have the negatively charged electrons. And those are the plums. Okay, so again, the positive charge is spread out over a volume with a diameter of a few angstroms for typical atoms, and embedded in this are the electrons. Okay, so that's the plum pudding model. I like to think of it as the chocolate chip cookie dough model. Okay, so then, early 1900s, a guy named Rutherford, what he does is he's trying to characterize and probe things about the atom, get more information. So what he does is he takes alpha particles and sends them through a metal foil. I believe it was a gold foil first. Now, what are alpha particles? Okay, well now, today, we know that alpha particles are positively charged. In fact, they are 2 protons plus 2 neutrons tightly bound together. At the time of Rutherford, people didn't know about protons and neutrons. They did know, though, that certain heavy elements would spit out these relatively large positively charged particles. They called them alpha particles. Now, they knew they were positively charged because of the way they bent in a magnetic field. If you remember in physics 2, you looked at charged particles bending in magnetic fields, and depending on which way they bend, you can tell whether they're positively or negatively charged. You can also get the charge to mass ratio by looking at how they bend. So people know that these alpha particles are relatively massive, positively charged particles. So what Rutherford does is he says, well, it'll be interesting to see how the positively charged alpha particle interacts with the positive charge of the atoms in the gold. So he takes a gold foil, right, and sends these alpha particles zooming towards the foil, and he looks to see in what direction are these alpha particles scattered. And he can look at 360 degrees, okay, with his setup. All right, now, he does the actual calculations. So knowing the approximate volume of the atom, and assuming that that's filled with a certain amount of positive charge, Rutherford works out the scattering mechanics, and he's expecting that because the positive charge is spread out over this entire volume, that these alpha particles should do quite a lot of forward scattering. The positive charge of the nucleus is going to slow down, right? Repel the positive charge of the alpha particles and deflect them. But because the positive charge, again, is spread out over the entire volume, it's somewhat diffuse. Well, Rutherford is quite surprised when he does the experiment that many alpha particles, in fact, are backscattered. Some right back along the incident direction, opposite direction of the incident direction. And Rutherford is really perplexed. In fact, he does the calculations and he says, look, to explain the backscattering of these alpha particles, this positive charge of the atom is going to have to be extremely concentrated to a very tiny volume. In fact, it has to be on the order of 10 to the minus 15 meters, which is a femtometer, F-E-M-T-O, a femtometer. So you can get backscattered when this incoming alpha particle basically comes right in along this line, gets slowed down and repelled by this extremely concentrated positive charge of the atom. Okay, now look at what Rutherford is saying, and again, he's quite perplexed about this, but he's saying that the electrons on this metal atom, right, they're flying around out here. So here's an electron. And the electrons, right, in what we would now call the outer shell, the dimensions of that outer shell are on the order of several angstroms, but the positive charge is concentrated to a diameter of a few femtometers. That is a huge difference in size, right? That's 5 orders of magnitude, right? An angstrom's 10 to the minus 10 meters, a femtometer 10 to the minus 15 meters. So you can see what Rutherford is suggesting, right? This is the advent of the nuclear model. So the positive charge is in fact located in a very small volume, which we now call the nucleus of the atom. Okay, and most of the atom then is really just vacuum. Right? So most of the volume of the atom is vacuum, free space. Okay, so this is, again, the advent or the beginnings of the nuclear model. So that leads to what's called the planetary orbit model then. All right, so early 1900s, we have the planetary orbit model. which says that the positive charge of the atom, is concentrated to this tiny volume, the nucleus, and the electrons are orbiting this nucleus, just like planets orbit the sun. So it's the planetary orbit model. Okay, so that's sort of the prevailing model after the famous Rutherford scattering experiments. However, there is a problem with this planetary orbit model that people soon realized, and that's when you try to explain how atoms emit light. Now, for a while, people were able to excite atoms electrically, and the atoms would then give off light in a gas. Neon signs use that all the time. Okay, so I'm going to show you guys on our course page, our course web page. If you scroll down, I have right here emission and absorption spectra of some atomic gases. So if you look at this first strip right here, this is excited hydrogen gas. And these are the colors or wavelengths that you'll see. You can see up here, this scale is wavelength. This is free space wavelength in nanometers. So if I see you in person, we'll actually do this. We'll excite some hydrogen gas, and I'll give you guys a fraction grading so you can actually see the different wavelengths at different angles, and you'll actually see these four what we call lines in the visible, although you might not be able to see this violet. It's very deep, so your eyes may not be able to pick that up. But excited hydrogen in the visible part of the spectrum only gives off four visible wavelengths. This violet, this blue, this sort of aqua, and this red. Okay, so it's very interesting. Here's excited mercury. Mercury gives off more visible emission lines, and this is neon down here. You can see that the mixture of all of these neon wavelengths is a deep orange. So if you look at just the light coming from a actual neon sign, it is that deep orange, but it's really a mixture of all these colors. Okay. And while we're talking about the emission spectrum, we might as well talk about the absorption spectrum. So if you take a gas and send white light through the gas and look at what comes out, that forms what's called the absorption spectrum. So this picture right here is a computer representation of the absorption spectrum of hydrogen. So you can see all the colors in the white light actually go through the hydrogen, except where these dark lines are. Well, these dark lines correspond exactly with the wavelengths that are emitted by the excited hydrogen. Okay, so the emission spectrum in particular is very hard to explain with the planetary orbit model. First, why are there only certain frequencies or wavelengths that are emitted? And in particular, there's a bigger problem, because if you take hydrogen, for instance, and people like to look at hydrogen because it's the simplest atom, right? We now know it's the most abundant form of hydrogen, a single proton with a single electron, right? Orbiting in this planetary orbit model. The problem is, if you try to explain how this can emit light, well, in classical electromagnetic wave theory, an electron moving around in a circle, it should emit light. Because if you think about it, this has a component that's vertical and another component that's horizontal. So you could always break the motion of the electron up into a horizontal and vertical component, and those components are oscillating, right? They're going back and forth, up, down, left, right. So a charge that oscillates should give off electromagnetic radiation in classical electromagnetic field theory. The problem is that we know that in that electromagnetic radiation, energy is being carried. So energy must be taken away from the atom, Well, if it's taken away from the electron's going to slow down, but if the electron slows down, it's going to end up diving into this positively charged nucleus. Because in the planetary orbit model, what you say is you need a centripetal force. Yes, physics 1, coming back to haunt you. So there has to be a force or a component of a force that points towards the center of that circle. Well, what you say is, yeah, that's just the electric force. The negative charge of the electron is attracted to the positive charge of this nucleus, right, along that radial direction towards the center, towards the nucleus. So the electric force is what gives rise to the centripetal force. And if this thing is going the way we're looking at it, counterclockwise, right now there's a tangential velocity, right? And a kinetic energy, 1/2 mv squared. The problem again is if this is radiating energy in the form of a light wave, this electron is going to lose kinetic energy, slow down, but that means then if it slows down, that centripetal force, that electric force, is going to pull it into the nucleus. Just like if a satellite starts to slow down, it's going to get pulled to the Earth via gravity. So this is a problem. A couple problems again. First of all, how does an atom even emit light without the electrons spiraling into the nucleus? Second, why are there only certain frequencies or wavelengths that are emitted? Okay, so this now sets the stage for Bohr's model of hydrogen. And again, he looks at hydrogen because it's the simplest atom. So what does he say? All right, so this is usually presented in a nice clean package called the Bohr's postulates. So let's take a look at the postulates, and then we're going to end this video. In the next video, we'll dive into more detail with the postulates and actually derive the energies that Bohr predicts for the hydrogen atom, which will enable us to figure out the wavelengths of those visible photons that are emitted. But let's talk about the postulates right now. Okay, so I'm going to go to the study notes, the summary notes, I should say, and here are the postulates in a nice clean package. All right, so the first postulate, and you should know these postulates, is Bohr assumes that this one electron orbiting the positively charged nucleus, it's in a circular orbit via the electric or Coulomb force. So you have a circular orbit, and the electric force, also known as the Coulomb force, is providing the centripetal force. Okay? All right, now the second one, he has to assume, because he knows that an atom has to be able to exist, right? The electron's not just going to spiral into the positively charged nucleus. So what he says is there has to be certain stable orbits with distinct energies. So there have to be certain orbits where the atom is stable. Okay, and the atom, or you can think of this as the electron, because we're going to assume that the nucleus is just sitting there. So the electron has certain energies, kinetic energies, and potential energies in these stable orbits. So the atom has certain energies in these stable orbits. Okay, well then how does light actually get emitted? Okay, so what Bohr says is, this is postulate 3, a photon, and this is where he brings in the new idea for, at the time, of the photon. A photon, a quantum of light energy, is emitted when the electron makes a transition from one of the higher stable orbits to one of the lower stable orbits. Okay, so the electron is in a more energetic stable orbit, farther from the nucleus. It can make a jump to a lower energy orbit, an orbit with a radius that's smaller than the first orbit. And in the process, it emits light, but in the form of a photon, in a bundle of energy. Okay, now, The reverse can happen, and that's how Bohr is going to explain absorption spectra. So a photon that comes in from another source can be absorbed by the hydrogen atom, but only if it can take the atom from a lower orbit to a higher orbit. So those orbits, right, they're only certain stable orbits. So there are only certain photon energies that can be absorbed because you have to go from a lower stable orbit to a higher stable orbit. Well, that explains why in the absorption spectrum of hydrogen, you only see certain wavelengths being absorbed. Because most photons are not of the right energy. Most photons can't take the atom from an existing lower stable orbit to a existing higher stable orbit. Only certain photons have the right energy to do that. So the third postulate is explaining why we have only certain wavelengths being emitted and why we only have certain wavelengths being absorbed. Sometimes you hear that referred to as discrete emission and absorption spectra. So the wavelengths that are emitted are discrete. There are only certain wavelengths. And the absorbed spectrum is discrete because there are only certain wavelengths that are absorbed. Okay. Well, then the big question is, all right, so we got this idea of these stable orbits, and we can sort of see how photons can be emitted and absorbed when you have transitions with these orbits. And in these orbits, we have the Coulomb force, the electric force, providing our centripetal force. But what determines these stable orbits? What's so special about them? And this is the one where Bohr, this didn't just pop into his head. He had to do some figuring to get this. But what he says is these stable orbits are determined by having only certain values of orbital angular momentum. They are quantized values. The orbital angular momentum is quantized. And this is the quantization right here. L, which is orbital angular momentum, which is mvr, I'll draw a picture in just a minute, can only have certain values. And those values are a positive integer n, that's not refractive index, no longer. That's a positive integer n times Planck's constant over 2 pi. The 2 pi pops up because of circular orbits, okay? So n times h over 2 pi. Now, this combination, h over 2 pi, occurs a lot in physics formulae. So somebody said, well, because we're so efficient in physics, right, let's just call h over 2 pi its own special symbol. And it's pronounced h bar. It's h with a little bar through the stem. So h bar is h over 2 pi, okay? All right, so this is the condition. All right, now, again, in the next video, we'll actually derive, using these assumptions, the allowed radii of the stable orbits and the total energy of the electron or atom in those stable orbits. But let me just draw a picture real quick before I end this, because it may have been a while since you've talked about angular momentum. You can define angular momentum for a solid, a rigid solid, like a board rotating around a bolt. And mechanical engineers, you probably remember this. You probably cover this more than other types of engineers. But angular momentum, we usually use capital L, is the moment of inertia of the object times the angular speed or velocity, I omega. But in this case, what we have is we have a point particle, right? So we have this electron orbiting in a circle with radius r, and let's assume it's going counterclockwise, so that would be its speed. You're assuming all the mass of the electron is at one point. In that case, the moment of inertia is just all that mass times the distance of that mass from the rotation axis squared. So the moment of inertia for a point particle is just mr squared. Omega, you might recall, is the tangential speed over the radius. So this is how you get the orbital angular momentum for a point particle is mvr. And according to Bohr, this can only be a positive integer, 1, 2, 3, 4, etc., times this h bar. This is the condition that determines these orbits. Okay, we'll pick up in the next video. We'll use this result along with the first postulate to do some figuring, some deriving. Okay, bye-bye.